All right, let's dive into something pretty fundamental, classical mechanics. It's this amazing set of rules that, believe it or not, explains everything from how a baseball flies through the air to how a planet stays in its orbit. So let's get right into it. So think about this for a second. What could a massive planet just hurtling through the vastness of space possibly have in common with the tiny, intricate gears inside a watch? It seems like they're worlds apart, right? Well, it turns out there's this single, incredibly elegant set of principles that describes the motion of both. And that, right there, is the heart of classical mechanics. It's the secret sauce that explains a just huge variety of things we see every day. Okay, so here's how we're going to tackle this. Think of it like opening one of those Russian nesting dolls. We'll start with the big picture. What is mechanics? Then we'll look at the split between classical and quantum. After that, we'll open up classical mechanics to see its branches, really digging into kinematics and dynamics. And finally, we'll see how this is all around us.
First things first, what exactly is mechanics? Well, simply put, it's the science of motion, force, and matter.
So officially, mechanics is the area of physics that's all about the relationships between force, matter, and motion. But what does that really mean? It means it's the bedrock of physics. It's what helps us understand and, this is the really cool part, predict how things are going to move and interact. It's basically the rulebook for the physical world, covering everything from, a baseball, all the way up to entire galaxies. All right, time to open that first nesting doll. See, the whole field of mechanics kind of splits into two totally different worlds. And it all comes down to scale. How big or how small the thing you're looking at is.
So on one side, you've got classical mechanics. This is the stuff that perfectly describes the world we can actually see. Planets, cars, a ball flying through the air. And it's what we call deterministic, which is just a fancy way of saying if you know what's happening now, you can calculate exactly what happened before and what will happen next. But then, on the other side, you've got quantum mechanics. This is the super weird, mind-bending stuff that takes over at the atomic level. It's all about probabilities, not certainties. For today, we're going to put that quantum doll on the shelf and focus completely on the classical world.
Okay, so let's pop open that classical mechanics doll. Inside, we find a few key branches: statics, kinematics, and dynamics. So classical mechanics is usually broken down into these three areas. You've got statics, which is all about objects that aren't moving, or are moving at a constant speed. Think of a bridge just sitting there, holding its own. It's super important, but the real action, the stuff we're interested in today, is in kinematics and dynamics. That's where all the movement is. And if you remember one thing from this whole explainer, make it this. The absolute easiest way to tell these two apart is to think of it like this. Kinematics is the how. How are things moving? And dynamics is the why. Why are they moving in the first place? One is pure description, the other is all about the cause. I saw this great quote on Reddit that just nails it. A user named Kisakaton said, "Kinematics is about motion. Mechanics is about forces." And that's exactly it. Kinematics is just the geometry of it all, but dynamics, that's where you bring in the forces, the pushes and the pulls that actually get things going. All right, let's dive into that first one, kinematics. We're talking purely about the how of movement here. This is the language we use to describe it. So the textbook definition says kinematics deals with describing motion without thinking about the forces causing it. It's really just focused on the geometry. A great way to think about it is like this. It's the vocabulary and the grammar we need to talk about motion in a really precise way before we even start to ask why it's happening. And that whole language, it really just boils down to three core ideas. First, you have displacement. That's just the change in an object's position. Easy enough. Then you have velocity, which is how fast that position is changing, basically speed with a direction. And finally, acceleration, which is just the rate at which your velocity is changing. Seriously, that's it. With just those three things, you can describe pretty much any motion you can think of. And here are the tools of the trade. These equations might look a little intimidating, but they are incredibly powerful. With just these, if you know where an object started and how it's accelerating, you can predict exactly where it's going to be and how fast it'll be moving at any time in the future. It's pretty much like having a crystal ball for moving objects. And here's a perfect everyday example of kinematics in action: projectile motion. Anytime you analyze the path of, say, a ball that's been thrown, you are doing kinematics. You're just describing its arc, its trajectory, the how, without yet getting into the why, which would be the force of gravity pulling it down. Okay,
So we've got the language down, we know how to describe motion, but that's really only half the story, isn't it? Now we get to ask the really big question. Why? Why does stuff move at all? And for that, we need to enter the world of dynamics.
And honestly, you can't have a conversation about dynamics without talking about this guy, Sir Isaac Newton. He's the one who had that incredible light bulb moment and connected force with motion. He literally wrote the rulebook for classical mechanics. And he laid it all out in his 3 laws of motion, which you've probably heard of. The first law, inertia, basically says that things are lazy. They want to keep doing whatever they're already doing. The second law is the big one, F equals ma. This is the powerhouse equation that directly connects force, mass, and acceleration. It's where kinematics and dynamics meet. And the third law just says that forces never act alone. They always come in pairs. Put them all together, and bam, you can explain why anything starts, stops, or turns. And a satellite is a fantastic way to see dynamics at work. Think about it. Earth's gravity is always pulling the satellite towards it. That's the force. According to F equals A, that force has to cause an acceleration. But the satellite isn't speeding up. So what's changing? It's direction. The force is constantly yanking the satellite sideways, forcing it to change its velocity's direction, and that's what keeps it locked in that perfect orbit. So this isn't just some abstract physics for planets and moons. Let's bring this all back down to Earth because mechanics is absolutely everywhere. So you might be thinking, okay, cool, but why does this matter to me? Well, these principles, which are literally centuries old, are the absolute bedrock of modern technology. Every time you see a skyscraper or a bridge, that's mechanics. The robotic arms that build your car, that's programmed with mechanics. Calculating how to get a rover to Mars, pure mechanics. Even understanding how your own body moves when you play a sport, that's biomechanics. It is the invisible blueprint for basically everything that's built. And when you boil it all down, what this gives us is an incredible power. The power to predict the future. I'm serious. Because it's deterministic, if you can just know all the forces acting on something right now, and you know its current position and velocity, you can calculate its entire past and its entire future. That is a truly mind-blowing concept. But, and this is a big but, here's the catch. Classical mechanics describes our world almost perfectly, until it doesn't. What happens when you get to the cosmic scale, like near a black hole? Or when you shrink down to the quantum scale, the world of a single electron? Well, at those extremes, all these familiar, comfortable rules, they just completely break down. And that opens the door to the even weirder, even more fascinating worlds of relativity and quantum physics. Makes you wonder what rules govern those places, doesn't it?